Hello and welcome back. This is Chris Burke and this is CSCE 155E, Computer Science 1. This is the first actual lecture where we're starting to go over the actual material here. Hopefully you had a good start with your first lab. Remember, I am watching the chat, but usually there's way too much chat on YouTube that I'm not probably going to be able to answer. So go ahead and answer each other if you can. But I will be monitoring Piazza, the live Q&A. If you have a question, I'll go ahead and be focusing on that. Okay. So today we're going to start out with the basics of C. We're going to look at basic variable usage, the basic operators that you can use, basic math operators, and basic input and output so that you can write your very, very simple programs. Before we do that, though, we need to have a little bit of better appreciation for what you were doing yesterday. Compiling and running. All right? So what you were actually doing yesterday, there was a lot involved that that was kind of opaque. You never saw it under the hood, and I want to walk you through that actually. So when you program something, programming languages are nothing more than plain text files. So source files are plain text files, right, containing computer code in a high-level programming language. Right? And this is going to be true of most all programming languages. You're going to be programming in the basic English ASCII text set. Now, some languages do allow you to, use UTF, which means for you can have a variable with an emoji name instead if you really want to, or you can program in CJK fonts, Chinese, Japanese, Korean fonts. It's not that usual though, so we're going to stick to the plain ASCII text character set, plain text. It is not a Word file. You don't program in Word. It is not a rich text file. It is a plain text file, and you have to edit it with a plain text editor. Notepad on your Windows machine is not a plain text editor. So that's why we encourage you to use either the CS50 IDE, which I'm going to be using to demonstrate here today, or as in video 1.3, we walk you through using Atom, which I'm actually using behind the scenes over here. It's being rendered over here with this thing as full markdown, but I'm actually writing in Atom.io over here. All right. So a source files have to be compiled because a source file, like we did yesterday with this hello world, this is not something that a computer can understand. This is way too high level. It's not exactly English. That would be the perfect programming language, right? If we could just tell the computer, like in Star Trek, computer do this for me, and it completely understood our natural language and did exactly what we told it to do. Unfortunately, computers are dumb. We have to explain it to them. And so, 50 years ago, 60 years ago, when computers started, you actually had to speak in binary. You had punch cards, and you punched a hole for 0. You left the hole, and punched no hole for 1, or something like that. And you actually programmed in binary, something that a stupid machine can understand. A high-level programming language like C allows us not to go all the way up to plain old natural language English, but somewhere in between. We can actually read this program. Okay. Source files have to be compiled into something that a machine does understand, an executable program, which is binary, right? Binary code. Okay. And the basic processor doing this, at least for C, is to take a source file, translate it into what's called assembly, and then translate that finally into a binary code. Again, this is kind of a progression of 60 years ago. You actually had to program in machine code with punch cards and stuff like that. Then they introduced assembly code, which is a little bit more readable, but still forces you to think like a machine. It's kind of like take this value and store it into this register, take that value, store it into this register, which is referencing actual circuitry on the machine, and then compare those two values and jump to this memory location, right? It's still going to be very, very arcane. It is not anywhere near English. That's why they introduced higher level programming languages, more and more abstraction, so that we can, as humans, understand it a little bit better. All right, and I'm going to walk you through the actual process so that you can see what each one of these things looks like. Okay. The command that you did yesterday or in your lab was simply just GCC. Oh, I'm not in the right directory. Remember, you need to change your directory into the directory where your files actually are. I'm currently in the home Ubuntu directory. I need to move into my code directory. That's where the hello world file is. ls is list. And now I can go ahead and compile it. Right, that was all just one operation. Now there's an a.out file that I can run, and that's what we did yesterday, or what you did in your lab. You can always clear out the terminal with clear. Okay. So what I'm going to do is I'm going to show what's going on behind the scenes as a step-by-step process. So one, which we already did yesterday, edit a source file, right, and make sure that it has correctly formatted computer code, correctly formatted in the language that you're using. You can assemble it, and I'm going to assemble it using GCC, but I'm going to give it, this is called a flag. This is telling it to do something different than the default. And so what this is going to do is this is going to end up compiling my program into assembly code. So GCC s hello.c. And this is just a demonstration. You wouldn't do this as a matter of course. You wouldn't do this normally. I just want to show you what it looks like when you do something like this. That produces this hello.s file. Right? And we can even ask the computer, what kind of file is that? Hello.s, it's an assembler code. It's plain ASCII text file. The code that we started out with was a C source file. Right? I'm just asking the machine, what kind of files are these? This is what it actually looks like, and it's still somewhat readable, right? These are kind of English words. Global, that's global. Main, right? Hey, there's that message that I was actually writing, and it's a string, right? A sequence of characters. But otherwise, there's a bunch of other arcane, like a sub Q, move L, move Q. I don't know what those are. But if I knew assembly, I know a little bit of assembly, but if you knew assembly back and forth, then you could still reasonably read this thing. It's still not something a machine can understand, though. So what you actually need to do is you need to compile that assembly code, and the way that we can do that is with the C flag, and that compiles, but it doesn't do what's called linking. So let's go ahead and try that over here. All right. That produces another file over here, hello.o. The .o stands for object. It stands for an object file. Let's ask the machine what kind of file that is. And like it says, it doesn't say object here, but it's an ELF 64-bit LSB relocatable blah 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 blah. It's now something that a computer can somewhat understand. Let's try to open it up over here. Right? Can't open it up because the file format is not supported. That means it's just a bunch of binary. Right? If I force it to list what the contents of it is, hopefully it won't screw up my browser here. But it's not a file. Okay, not a text file, so it's not. I can't force it to do that. But I can use another utility. I will use what's called a hex dump. All right, hello.o, and you can see that it's just a bunch of data, right? A bunch of zeros and ones. Now this is hex data. That's why it's the utility is called hex dump. That's hexadecimal. Decimal is, we are humans, we count in base 10 because we have 10 fingers and 10 toes. 0, 1, 2, 3, all the way up to 9. Computers count in binary. 0 and 1, 0 and 1, and with overflow. But you can also compactly represent this using base 16, where you use 0 through 9 and then A through F to supplement that. And that's what you're seeing right here. Of course, I can force it to be a binary using another utility here, hello.o. Right? And you can see there's its binary representation. And yep, some of it's still readable over here, but it's just, for the most part, it's just a bunch of binary. Lots of zeros, that's padding and stuff like that. But now it's something that the machine can somewhat understand. It's still not runnable. If I just said, hello.o, permission denied, it's not actually going to run. What I need to do now is I need to link that in. Remember, in our original file over here, we brought in a bunch of external libraries, the standard library and the standard input-output library. Our code here is just a program without those libraries. We've compiled this code. Somebody else already compiled that the standard libraries, and it's available on this system for us. They already did that work for us. What we need to do now is link these together to actually produce an executable file. And to do that, all you have to do is gcc hello.o, and that produced this a.out file. Right? But of course, again, you don't have to do this piecemeal. You have to, assemble it. Then you have to compile it into assembly code. Then you have to assemble it into machine code, and then link everything. Right? You can all do that with just one command, gcc, and it does all that process in one shot. Okay. So to review on our notes here, let me go back over here. There we go. Let's see. There we go. Compiling it produces an object file, hello.o. You can view it using hexdump, or I was using another utility called xxd. You can also then link it with external libraries. Right? But of course, the way that you're going to usually compile something all at once using gcc hello.o, or .c, excuse me. That does it all in one shot. You don't have to worry about it then after that. Right. Let me give myself some more room here. There we go. Now it'll always pop up to the middle. All right, so now that we understand that kind of a background of, again, I am monitoring. This thread is for the Q&A, or you can start a new one if you want. Should we be taking notes during lecture? It's on you, right? Usually, there's a lot of research showing that if you take notes, not even necessarily that you're going to use the notes, but just the simple fact of hearing something and then immediately regurgitating it onto notes or typing it. The research is still out on which is better, actually writing it by hand or typing. That's a personal preference. But the research does show that the simple act of taking notes helps retention, helps understanding. It also forces you to be engaged. And so if you're playing a video game in the background and not taking notes, you're probably not going to be as engaged in what I'm saying, right? You're talking about games before. I have no, what was it? A skip, what? I have no idea what a spike rush is. There we go. I have no idea what that is. Program basics. All right. So what I'm going to do is I'm going to pull over another program, not a hello world program, but a full program that actually does something, okay? I'm going to go ahead, let me go ahead and bring it over into our IDE here instead. I'll create a new file, and I'll name it foo for now because I want us to look at this file and just understand, just by looking at the file, what it kind of maybe does. So let me go ahead and close these out since I don't need them anymore. And then we'll rename this file later on, okay? And I'll go ahead and update this date here to our date, 9 and 18. Right? By the way, two things to note: that you should be using this proper ISO formatted date in your daily lives even. It's the year, month, and day. Everybody else is wrong. Americans are wrong, Europeans are wrong. Only the computer scientists write their dates correctly like this, so that they are in lexicographic order and sortable. All right? You might want to get into that habit. All right. So what does this program do? Well, from this, we don't even have to read a single line of code, do we? All we have to do is read this first sentence. That's documentation. That's telling us what this program does. And so that's the first basic thing in a program. What are comments? Right? Comments are human readable messages embedded in code. Right? You can have single line comments begin with a what are these things again? Are those backslashes or forward slashes? Again, the guy is facing to the right, so he's leaning forward. Those are indeed forward slashes. Anything following them on the same line is ignored. It is not even the compiler completely ignores it, strips it out. In fact, the preprocessor probably does that. We'll talk about that later, what the preprocessor is. There are even more steps than my demonstration had. and they're not even part of your end program. So it doesn't matter if you put 5,000 lines of documentation in your program. It's not going to make it less efficient. All of those are stripped out in the final executable. All right. All right. All right. I'm going to go ahead and resolve the questions as we go along here. Okay. You can have multi-line comments. Begin with a /* and end with a */. Anything between them, even if they are on multiple lines, is ignored. Right? And so that's what I did up here. Right? Here is a multi-line comment that begins with a /* and a * ends with a */. And you can see in my IDE here that it's been highlighted in blue to indicate that this is indeed a comment and it's ignored. Okay. Down here I've got a single line comment where I'm saying prompt the user for input. Okay. So there are some examples already in the example that in this little program that we've built. Doc style comments are multi-line comments with a particular formatting. Right? They have a vertical line of stars and are intended to be used for documentation. That's what the doc style is. I believe that this originated with Java and Java docs, but it has been adopted by many different programming languages. Java docs, CPP docs, PHP docs. Everybody has a doc style commenting system now. And you can see what it looks like here. Up at the top, I've got a header. That header is intended to give documentation of who wrote this, when did they write this, what does this program do. And documentation basically is intended for humans to be for human consumption, so that they don't have to go down and read these 30 or 40 lines of code and say, okay, well, we've got a variable here, miles, kilometers, probably something to do with distance. Okay, we read in from the user an input, and what do we read in? Well, it looks like we read in miles, and then we convert miles to kilometers, and then we print that out, right? I could have just read this one single sentence up here. And that tells me what it is. And that's the point of documentation. All right? Comments, especially documentation, is intended to tell the user, that is you or other developers, right? The why. Why did you write this code? And the how, right? What does this code do? What does it, or not what does this code do, but how, as in, if you've got a very complex algorithm, then you can document that algorithm. Like I use a fast Fourier transform to do the signal processing, and so here's the algorithm. Here's documentation for the algorithm. Here's the Wikipedia page for this algorithm. Read more about it here, right? That tells the how, not the what. Right? Code should be self-documenting in that regard, right? That is, code should tell you what, right? And the what being that if you, now I'm not expecting you to understand what this program does entirely yet. Definitely by next week you will. But if you take a developer that's been developing in C for at least even a month or two, your code should be self-documenting and self-explanatory to anybody who is well-versed in that programming language. They should not have to learn, they should be able to read and understand your code just by looking at it line by line. That's what should tell them the what. All right. So what does that mean for you as starting out as a beginner? Well, this single line comment here, right? Let me go ahead and increase the size. I don't know what the resolution is on YouTube right now, but how is it? Somewhat viewable. Yeah, okay, but increasing the size will probably help. Again, if I'm not coming through or the resolution is bad, let me know and I can try to change it. All right. So this single line comment here is not something I would ever do in real code. This is your first real program here. So I'm demonstrating how you can write a comment. Every single line does not need a comment, right? Every single line should be self-documenting. Once you learn what the printf function does, this is completely unnecessary to write this comment here. Once you learn what scanf does, it's completely unnecessary to have this comment here. In fact, neither one of those comments should appear in actual real code. They're self-explanatory. Okay, that's what we mean by self-documenting. Now, if you did some weird printf that you hacked together a bunch of assembly or something like that, that's not self-documenting, and so you should put some comments in there. For the most part, for your first few hacks especially, we're looking for this at a minimum. Every program that you write should have some documentation. Of course, the simpler the program that you write, then all that's really necessary for like a Hello World program or for this program is just the header documentation. Tell me who wrote this. Tell me what this program does. Okay? All right, moving on here. What are these things? I told you on Tuesday, I guess, that those are the libraries that we're bringing in. In C, those are called preprocessor directives. All right? Preprocessor directives. Right? For you, in your generation, they look like what? Hashtags, right? Well, why do we have hashtags, by the way? Hashtags date back to IRC. IRC is Internet Relay Chat. You would use those for particular channels. If you're on Discord, you have different channels in your Discord, like hash random or hash introductions or something like that. That is nothing new. That dates back to whenever IRC was created, Internet Relay Chat. That's how IRC channels were designated. In this case, they use the hash here to and a keyword include to include an external library. Right? So that's one usage of them. Let's see. Preprocessor directives are directives that to the compiler to do something before it starts compiling. All right? And they can get quite complicated. You can have what's called conditional compiling. We won't get into that in this course. But what we did, how we've used them so far in two ways here, is that you can bring in or include external libraries, so you don't have to start from scratch, right? Maybe you're really jazzed about writing a bunch of assembly code to actually print out every single little pixel to the screen with a bunch of system calls. No, you're not jazzed about doing that. That's why we bring in those external libraries, so that we don't have to write code to print ourselves. We can just use that printf, which is in the standard input-output library, using the include along with the library name surrounded by Langle-Wrangle. Right? So those are two new words for you maybe. Langle-Wrangle, right? The less than sign and the greater than sign. Well, if it's in a math equation, of course, you say less than or greater than. But if it's in a completely different context, we call them Langle-Wrangle, right? Left angle and right angle brackets, right? That's actually from LaTeX, but don't worry about that. So again, example, we can include something that we haven't seen before here. I'll include the math library. Right? So are you jazzed about writing your own sine functions or your own square root functions? Right? Probably not. It's something that we may do later on as a demonstration, or maybe in one of the hacks, I forget. But that brings in the math library. You've got access to sine, cosine, and all of the basics, all the basic math that you would find, say, on a Texas Instrument calculator or just a regular calculator, right? A macro, these are called the preprocess. These are known as macros. Right? So if you've never heard the term macro before, a macro is just something that it's a defined process that the computer can repeat. So if you've ever done like some advanced Excel programming, you can actually record yourself of an action, doing an action, like take this cell and put it over here, and then add it to this cell and put the result over here. You can actually record yourself doing that, and so that that action can be recorded as a macro that you can then repeat over and over again, so you don't have to do that click, 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 click over again, right? Sorry, these are not known. You can also define define macros, right? These are using define. And that was the other preprocessor directive over here. So let's take a look at it. Define KMS per mile. What do you think that stands for? Well, that's a good variable name. KMS, kilometers per mile. The context tells you that those kilometers. Maybe a slightly better variable name here. It's actually not a variable, but a slightly better identifier would be kilometers per mile, right? And I'd argue that that's probably a little bit better. But in the context of miles, I mean, what else could KMS be, right? You've got a mile there. As long as you don't shorten both of them to M, like, oh, kilometers per meter, or what is that now? Yeah, but in the as long as the code is self-documenting and the context is clear, then you can shorten variable names. You're not paying by the character though, so you might, if you're ever unsure or in doubt, yeah, then you can go ahead and write out the whole thing. Again, you're not paying by the character. So this is a macro. What it means is anytime that you see the identifier KMS per mile in your program, replace it with 1.60934. So down here where we compute the kilometers per mile times the miles, then what the preprocessor does is it does a cut and paste. It goes in and says, oh, okay, well, I know what that is. That should be 1.60934. I'll go ahead and replace it with that. That's what the preprocessor actually does, right? I'm not going to do it because I don't want to mess up the code here. But that's what a macro is, a cut and paste, right? A macro using define is essentially a cut and paste. Why would you want to do this? Right? Why? Why do I have this when I can just write that number, right? Forget about the macro. Let's go ahead and just write that number. Right? Now, if you were just if you just jump to this one line, would you know that there are 1.60934 kilometers in every mile? Well, if you do a lot of running, maybe you do. If you do a lot of distance stuff, maybe you do. Maybe you can read around the lines and say, well, kilometers, miles is probably distance. I'm guessing that maybe there's 1.60934 kilometers in every mile, right? That's what we call a magic number, right? That it means that you have to think about what it actually means. Whereas KMS per mile, I could just read that, right? It is much better to use an identifier like this than this magic mysterious number. Where did that come from? Now, certain numbers like 3.14, oh, that's probably pi. 2.71, oh, okay, well, that's probably e. What about 0.9345? I have no idea what that is. And I just made it up anyway. So if you've got, avoid magic numbers, right? It allows us to use identifiers for constant values, right? Using macros or using defines avoids magic numbers. Values whose purpose is not immediately clear. Right? Also, another reason is what if it changes? Now, that's an approximation. I don't know how many actual, let's just ask Google. 1 kilometer to mile. Actually, I've used DuckDuckGo, so, oh, sorry, no, 1 mile to kilometer, the other way around. Okay, so it's 609,344. I want that to be slightly more accurate, right? I can go ahead and add a 4 in one place. Now, granted, in this simple program, I'm only using that value in one place. But you can imagine that if I had a much more complicated program where I was using this variable, this value over and over and over again because I was converting miles to kilometers for acceleration and converting them miles to kilometers to compute F is equal ma, force, right? Mass times for acceleration, right? If I was using it in 50 different places and I wanted to change the value to make it more accurate, add more significant digits or sigdits or sig figs, so there we go, that sounds better, then I would have to change it in 50 different places. Whereas if I use a macro, I only have to change it in one place, and the preprocessor takes care of all the other work for me. Right? So that's another reason, right? It keeps such values in one place, right? Changing them means only one value gets replaced instead of many, right? So that's another reason that you would want to use this stuff, okay? And again, there are other preprocessor directives, but we're not going to cover those. Maybe we'll cover one or two later, but this is all you need for now. Right? By the way, I want to go back a little bit, and what about that math library? I wonder what's in there. Right? I'm going to show you a trick here. These are called the man pages. Well, what about sine? There is no sine. Man, sin. Right, sine, sin, or sine, right? There's the sinusoidal function, the sine function, right? And there's a whole documentation down here that, well, it's in the math library. All you have to do is include the math library. How does it work? These functions return the sine of x where x is given in radians. Oh, okay. Remember that you can have radians in a circle, 2 radians, 2 pi, or you can have 360 degrees, right? Just like the reason that we use kilometers in scientific applications instead of English measurements, miles, we also use radians in scientific applications. Scientific and engineering and in real applications, we use radians, and that's why it works in radians. So if you've ever got degrees, you need to convert that to radians and then use the sine function if you want to use it. Okay. Unlike your standard TI-82 calculator or whatever you use. On success, these functions return the sine of x, etc. There's possible errors. X is nan if a nan is returned. If x is positive infinity or negative infinity, domain error occurs. Okay, I wonder what that means. I wonder what nan is. Nan is not a number, right? And a bunch of other just documentation here. And related things. Oh, we also have arcsine and cosine. We also have tangent and cosine, etc., etc., etc. These are the man pages, and you can access them using man and then the keyword. What about math? Man math.h. I don't know if it'll do that. Yeah, it won't do that. You can look up specific functions. You can tell me all about printf if you want to read all about that, right? But man stands for manual. So if you ever need to look something up, you can use the man pages. They're usually on Google as well. So man pages for sine, right? And that'll pop up right there, right? Along with a bunch of weird comic booky stuff there. So there's the exact same thing, but on the web instead, if you want to read it that way. So those are the man pages. And lots of there is a square root function, sqrt. We'll talk about that later. Okay. All right. Let's see. There's one question here. Why don't we just define a variable instead of define? Good question. Variables, you can if you want to, but then if I did it that way, then it can be changed. So I could do something like this: double kms per mile is equal to this, with a semicolon here at the end. But now the problem with that is that I can always change that. I can say, well, okay, now we live in a world where there are only 2 kilometers per mile, right? That's a variable. I want to make that constant, and so you can do that by making it constant. But now you've got a variable. Now you've got other issues of can that fit into a double, or is there a truncation? Is there a different representation, et cetera, et cetera? For the most part, for everything that you're going to do, yeah, it's probably going to be the same. But there are some situations where you want to use a macro instead of defining a constant like that. Okay. All right. Good questions. Do preprocessor directives need to be ordered in a certain way? Can define come before and include? Generally, you put defines after includes, but you could, in this instance, you could move it up. It doesn't really matter. But stylistically, defines usually come after. Stylistically, though, you want to structure your program more modularly. We'll get into that later when you define your own header files and source files and then separate everything out into different files. We're keeping things simple for now. Okay? All right. What's next in our program here? Now we've got our main entry point. Right? The main function is always the starting point for any executable program. Right? For now, ignore the argc and argv. Oops, sorry. There we go. These are command line arguments. We will talk about those later, and of course you've got the videos that explain them. But these are command line arguments. We're not using those yet, but you of course certainly will be eventually. In Lab 2, in fact. You'll get exposure on how to use these. What else do we see here? Right. I see commas. Right? I see semicolons. I see white space, right? That I write a line of code and then I put a space between it. I write another line of code, put a space between it. This is kind of double spacing. It's not necessarily something I would do, but I do see different stylistic aspects here. I see basically punctuation, right? So semicolons end every executable line of code. Right? And I'm going to emphasize executable line of code because later on we are going to look at lines of code that are not executable. They're like conditionals. If this condition, then you do this. If this other condition, then you do that. And those are not executables. That's a decision process. That you do this or you do that. This or that, those are the things that are executable. So there are some things that do not have lines that do not end with a semicolon. In particular, we don't end this opening curly bracket here or this ending curly bracket with a semicolon. Only executable statements like declaration of variables or print this message or read the input. We have semicolons at the end there. Why? Right? They are like periods at the end of a sentence. Right? Ants. All right, they don't like that. There we go. I don't know how to spell. You'll have to bear with my spelling. So program code, again, is very, very much like English, or at least people try to design languages that are closer to English than the machine code. And so they tend to put in aspects of English, like say organizing things into sentences and having a delimiter, right? You end a sentence with a period, you end an executable statement with a semicolon. You organize code into blocks of code, and just like you organize an essay into paragraphs, right? There are various ways that computer code is very much like English, right? Commas delimit lists, right? For example, up here we have int argc, comma, char, star, argv, right? That's a delimiter. That's separating those two things. Here I'm declaring two variables, which we'll talk about later, but I need a way to delimit them. I need a way to say I want this variable and this variable and this variable. In English, we say I want I want ice cream, comma, cake, comma, and fudge, all right? Brownies, there we go. I have a comma there, right? Now, that last comma is an Oxford comma. Whether or not you like the Oxford comma, who knows? I don't care. But in code, you certainly need commas between everything. If I wanted another variable, then it would be, of course, another comma. I can't just have something like this, okay? I've also got spaces, but in general, white space doesn't matter. You insert white space to make things more readable, right? White space, in general, does not matter, but you should include it to make your code more readable, right? Here I've double spaced everything. It's not always that necessary to do that. In fact, I like to chunk pieces of code together. This chunk does these 4 lines are related because they do one operation. I'm going to chunk those together. Then another space. These 4 lines do something, and I'll chunk those together. These 7 lines do something, so I'll chunk those together, separate those out by spaces. Certainly, you want horizontal spaces. It does not look good if you do something like this. Right? So, spaces are your friend. Spaces make things more readable. Okay. Let's see. Still no question. No more questions. Double quotation marks. Delimit strings, which are sequences of characters. Like in my message right here. Double quote for please enter miles, just like we had double quotes for hello world. That's a string variable. In fact, my IDE here, the CS50 IDE, is highlighting those in green so that you know that this is the end of the string. If I forget that double quote there, right, then, oh, it's not doing it. Usually an IDE will then highlight everything else in green because you forgot to end it there. But apparently this is not doing it. Okay. Let's see what else. You have blocks. You have blocks of code which begin and end with curly brackets. Right. Will the notes be posted? Yes. Oh, is the live stream lagging? I've only got 0.1% dropped frames, so and otherwise everything's looking good. 2800 kbps. OBS is chugging along here. So, okay. What happens when you use single quotations for a string? You can't. Single quote in C, that is. Single quotations are for single characters. So if I tried to do that here, then this is definitely a compiler error. Right? Let's go ahead and try to GCC foo.c, and it's not going to understand that. Okay. In fact, there's another problem up there. Oh, I forgot. I was editing this. I don't need that right there. There we go. And it'll complain about that because this is not a string. Single quotes are used for single characters in C. Now, some programming languages do allow you to use them back and forth. Many like Python or PHP or something like that. As long as you start it with a single quote and end it with a single quote, that's a string. In Python, as long as you bring it with a single quote, double quote, and end it with a double quote, that's a string, right? In C, however, a string is always double quotes. Single quotes are always single characters. We'll talk about single characters later on. Okay. All right. There we go. All right, you have blocks of code that begin and end with curly brackets. That's right here. Here's this block of code that begins with that opening curly bracket. There it ends with the closing curly bracket. This entire block of code right here is my main function. Right? You can have nested blocks, which we will have later on, where basically that creates an entirely new context, and it's a different function. Or when we write, say, loops or conditionals, we'll block that off with opening and closing curly brackets. That is like the paragraph organization. That a curly brackets define a block of code. That block of code is kind of like a paragraph. Okay. Let's see, what else do we see? In general, white space doesn't matter, but styling. Use white space, use horizontal white space when appropriate, when, in a list after a comma. Use vertical white space when appropriate, if you want to chunk code, not necessarily blocks of code, but chunks of code. Vertical. Right. Use indentation to indicate blocks of code. Right. That's a style thing. You don't have to do that. I could probably take out every single white space character in this program and it would still compile. The computer would still understand it. But it would be very, very confusing. Right? It would not be readable at all to a human anymore, right? I could put everything onto one big giant line. That's not going to be readable. I'm going to undo that immediately, right? Don't do that. In this block of code right here, I have indented everything, and everything is at the same indentation level. In this case, I've chosen to indent with 2 spaces. That's just my personal style. If you choose to indent with a tab, that's fine too, as long as you do it consistently. If you want 3 spaces, okay, well, fine. I want 3 spaces, then everything else needs to be 3 spaces, right? And do we have a format? Oh, no. Some IDEs will allow you to hit a button and just reformat everything automatically for you. Apparently, this one, CS50, does not. So there are some external tools that are available in Canvas that you can do that with. I may go over that later. Okay. So use indentation to indicate blocks of code. That's good styling. So I'll relabel that as good styling. Good styling is variations on style are okay as long as they are used consistently, right? So you should not have, oh, I want to for my first 10 lines of code, I want to indent by 2 spaces. Then for my next 10 lines of code, I'll go ahead and indent 3 spaces, right? Because I'm just feeling different for those other lines of code. No, it has to be consistent. You should use the same style throughout your entire code base. A lot of times when you actually work on an actual code base, they're going to have what's called a style guide anyway, and they're going to dictate the style. No, all our code at this company needs to be two spaces of indentation, or we use tabs at this company. All right, really, those are style guides, and there are a lot of competing style guides. There are Google style guides. There are GNU style guides. It really doesn't matter if which one you adopt, because eventually you're going to have to conform to whatever style guide and project that you're using. Anyway, but choose a mainstream one and stick with it. Just get into the habit of writing readable, good code from the beginning, and you won't have much to change, right? There's a lot of other stuff that we're kind of glossing over, but that's okay. There's several reserved or keywords, right? For example, double. I wonder what that is. Int. Right? Hopefully there's a hint there at what int is. Integer. Printf, etc. Each one of these is either a reserved word that you can't use or that you can't redefine. For example, include and define. Those have very well-defined meanings. Int and double, those have defined meanings that you can't change. Printf is a function that's in the standard input-output library that you can change, but then you're breaking everything. So I'm not even going to show you how to do it. But you can do it. You'd have to there are some easy ways that you can do it, but I'm not going to. But anyway, so there are also keywords that you can't use and that have a special meaning to the language itself. KMS is a variable name. It is not something that's built into the C programming language. Instead, it represents kilometers, right? Miles is a variable name that we've defined up here, and it's not something that's built into the language. Double, however, is built into the language. That's why it's highlighted in blue here. C compiler understands what that means, and you can't or you shouldn't change its meaning. Okay. All right. That's the basic anatomy of a C program. Now let's start looking at the smaller details in there, including variables. Right? A program would not be of much use if we didn't have variables. In math, variable is something that can vary its value. In mathematics, if I say something like f of x is equal to x squared, right? There we go. X is a variable there, right? Depending on the value that you plug into x, you get a value for that function. If I say that x has a value of 2, then that function squared gives me a value of 4. If I say that it has 3, then it gives me a value of 9. It's kind of what we mean when we say a variable in C. But we have to understand what that means at a little bit deeper level. First of all, C is a statically typed language. Right? Don't worry about what that actually means. Worry about what it means in practice. Basically, you have to declare a variable before you use it. Right? When you declare a variable, you declare a variable's name or identifier. Right? That's the technical name. We'll just call them variable names instead of identifiers. And you also indicate its type, right? Which cannot change in the program in the after declaration. Right? Okay. Now, to understand this, let's look at some of the variable. Let's look at a couple of variable types. Right? The first variable type that we're going to look at is an int. This is an integer that can represent a limited set of values. In particular, let's see if this works. There we go. Well, I want to go to the next line so that it's... There we go. Oh, it still doesn't look all that great, but so be it. It's an integer. All right, fine. Let's use actual LaTeX on this. There we go. That looks much better. This is less than or equal to, and this is less than or equal to. There we go. All right, it can represent a range of values, and that's because computers are finite objects. Computers hold memory, as you know. Even if you've got a, I don't know how much memory my MacBook has, but I don't know what's standard now. But if you want to flex, go ahead and put it on the chat or whatever. How much memory, how much RAM does your laptop have, or does your desktop have? Usually, say it's 4 gigabytes or 16 gigabytes or something like that. Doesn't matter. That's finite, right? It can only hold so much. Variables are 128 gig. Okay. Oh, you don't have that much terabytes of RAM. Yeah, right. That'd be a fortune, right? Anyway, I doubt that you'd have any motherboard that would accept that much RAM. You need a huge RAID or not a RAID, but you need a pretty damn good setup, supercomputer kind of thing to have that much shared memory, RAM memory. But anyway, and even then, no operating system would have would make it a terabyte that big addressable, right? Yeah, download more RAM, exactly. So anyway, the point is that memory is a finite thing. You can only hold so many bits to represent a number. And with an integer, it's at 32 bits. An integer, a 32-bit signed twos complement integer, right? Again, don't worry about what that means. When you take computer architecture, you'll learn all about that. Just understand that there's a sign bit that is 1 if it's negative, 0 if it's positive. That's why we can represent a range of negative values over here and a range of positive values. But the remaining 31 bits can be used to represent the actual number. Since it's base 2, that means that we can represent 2 to the 31st values, right? And if we look up, I'm going to go ahead and open up Wolfram Alpha here. 2 to the 31st, that is about 2.147 billion. Of course, we need to represent 0, so there's 1 less. And that gives us this value right here. This 2,147,483,647. That's the maximum value that we can represent with just an integer. Likewise, we can go to the negatives with that sign bit, flipping it from 0 to 1, and then we can represent 2 to the 31st, which is that full 2.147 billion all the way up to 8. Why? We don't need to use a representation for 0 there. So we get 1 extra on the negative end. That's for 32 bits. There is a 64-bit integer called a long. You can have a long. You can have a long int, right? You can keep going up, but it's still going to be finite. If you have need of representing numbers that are millions and millions of digits, then you need to bring in a library to do it. We're only going to focus on integers for now. And the other number that we're going to focus on, the other number value is a double, right? This is a floating point number. It's actually an IEEE 754 floating point, a 64-bit floating point number. IEEE 754 is just the standard that dictates how these numbers actually work. What happens when you add two of them together and there are round-off errors? All those rules are defined by that standard. Don't worry about that. Here's what you should worry about. It is a decimal number that has about 16 to 17 digits of accuracy. Right? It doesn't matter if those it's a huge number, like 10 to the 300th or something like that. It still will only represent the 16 most significant values, digits in that number. It doesn't matter if it's a really tiny small number, 0.000000001234. It still will only have 16 digits of accuracy at the low end. The most significant digits, there are only 16 or 17 of them. Right? And then at that point, at the low, then you start to lose accuracy. And there are some numbers that are not representable at all by these numbers, like 1/3. Why? 1.33333333 forever, right? Eventually, if you only have a certain number of digits, 16 digits, well, then that last digit is going to have to go down to 2, so 333332, or it has to go up to 4, 33334, and then it ends, right? And that's the end of that representation. Okay. There's a good question on. There is also a float. There's float. Float is a 32-bit floating point number. We'll not use it in this class, but it was so it's because it's less accurate. It's only going to have 8 digits of accuracy. Now, floats are perfectly valid if you're doing, say, gaming programming. Where the number of digits of accuracy that you need to compute, a pixel, you don't need that much, right? You don't need to calculate distance out to 1 micron versus the whole universe or something. For the most part, a double will give you the accuracy that you need. Floats are a little bit more efficient, but they're also less accurate. There's always a trade-off here. So we're not going to cover floats. So we're not going to use them in this class. If in certain applications, if you want to use them, great. But your values are probably not going to match those on the web grader, because the web grader is going to use the double, which is more accurate. All right. All right. Oh, there's a question here. Oh, okay. My typing is lagging. Well, that's because it's updating. It only updates every fourth or fifth keystroke, and then it updates. There's nothing I can do about that. It's not actually lagging. I'm typing and it's perfectly fine over here on one screen, but when it renders over there on the screen that you see, that's where the lag comes in, because it's only going to render it every like other second or something like that. I don't know what it's set to. All right, so that's integers, doubles, and finally a char. Right. This is a single character value. In fact, it's a single ASCII text character value. Right. This is not something that we used in our program before, but we can go back and check it out now. Actually, yeah, let's go ahead and I'll do it right here. Right. So I can go ahead and create a character value, char, initial, my first initial, right, C, and that is a single character value, like we talked about before. Double quotes for strings, multiple characters, single quotes for single characters, and you can use a char here that value is actually a single byte, right? And what does ASCII mean, right? ASCII is a character set that is actually quite old. It predates modern computers. I think it goes back to the Truman administration. Let's find out. Okay, that's not the Wikipedia page. You're gonna have to look. You're gonna have to look at it yourself. But ASCII stands for American Standard Code for Information Exchange. Way back in, say, the 50s, I don't even remember when. They saw a need that we need to standardize our character set, and of course, since it was an American standard, it focused on the English alphabet, A through Z, capitals, lowercase, our Arabic numbers, etc., etc. And it also established several control characters here. The null character, which we'll talk about much later on. You can get characters like the bell. If you printed that character, your computer's supposed to ding, right? Think back to 1950s, where computers were not that common. But what was common? Typewriters. That's why you have what's called a form feed, a line feed, and a form feed, or a carriage return right here, sorry. Those are different, right? Because if you think back to how a typewriter works, you can actually twist the drum to go down to the next line, but stay in the same column. Or you can twist, typing, and the drum goes, and then you hear a ding, and then you have to push it all the way back. That was a carriage return. And so it was very, very much focused on typewriters at the time because that's what existed. And so they set out this character set based on typewriters, basically. And let's get a much better representation here. This one over here. And then, of course, you can read all about it on Wikipedia page here. 19... whatever, 1968. Okay, I'm sure that was much. 1956, it looks like. Before that, they even had standards for keyboards. So these standards go back a long, long time. Let me go ahead and focus in over here. They're all in the standard ASCII text character set. There are only 128 characters, and each one of them has a decimal number associated with them. For example, the space bar, right, just typing a space, that has a value of 32 associated with it. That capital letter that I had for my initial C, that has a value of 67 associated with it. So at the end of the day, everything in a computer is binary. Everything is a number in a computer, including our own alphabet here. Capital S, lowercase a starts at 97, etc. The thing to take away on this is that characters are numbers, and numbers are ordered. Therefore, characters are ordered. You'll see here that they built into the standard that it goes A through Z. Capitals come before lowercase values. Certain punctuation like spaces or exclamation point or the numbers, the character numbers are in order, and they come before letters over here. And this is what we call lexicographic ordering. It is not exactly the same as alphabetic ordering because if you look at a dictionary, all the A's are together, whether or not it's a capital A or a lowercase a. The dictionary orders without regard for case sensitivity. But our ASCII text character set does make a difference, and the capital A comes before the lowercase a. In fact, the capital Z, which has a value of 90, comes before the lowercase a, which has a value of 97. That's something that's going to come into play later on when we start sorting things and doing string comparisons. But otherwise, you need to understand that it's an ASCII text character. It's not one of those newfangled modern text characters like an emoji with smiley face with sunglasses. Right. There we go. Well, here, smiling face with sunglasses emoji. That also has a numerical value associated with it. Are they going to tell us what it is? There's the numerical value associated with it. The U there is indicating that it's a Unicode character, UTF-8 or whatever the standard is, and then it's in hexadecimal, 1F60E, right? That's a number that's much larger than 127, which the ASCII text character set here goes from 0 up to 127, and then it stops. Well, they didn't have emojis back then. They have an extended character set that looks something like this. They said, well, we need more characters, right? So we're going to go ahead and put diacritics here. E's with umlauts, U's with umlauts, right? And so that goes from 128 to 255, and then some pictorial characters over here. That's still not enough because we have Japanese, Korean, Chinese fonts. We have Egyptian, ancient Egyptian. We have they tried to do Klingon, by the way, but they were rejected because it has to be a real language or used in a real application. But for some reason, they reject Klingon, but they're perfectly happy with emojis and distinguishing between whether or not they're happy and whether or not they've got sunglasses on them. They introduced the Unicode, the extended Unicode character set, which has support for several million characters. Many of them are completely unused still, and in fact, you can actually write a proposal to include your own to create new characters and descriptions of new characters, and then register them in that standard. That's why somebody wrote a standard for Klingon characters, and it was rejected. But pretty much any actual language that's used on Earth has a Unicode setting for it, including Ancient Egyptian, right? All those pictorial characters. Okay. All right, in our last 10 minutes here, let's go ahead and look at some examples. So, what do we mean when we declare a variable? Again, you have to provide the type and the name, and then you also can provide a value for it. So let's declare an integer variable. So the way, I'm putting that in a comment so that it's readable, and I can go ahead and increase the size over here if you want, since it's kind of grayed out there. Int x. Right? So int is the type, then x is the name of the variable, and then I end that with a semicolon. Or you can declare, you can set a value later on using the assignment operator. The assignment operator is just the simple equal sign. X is equal to 10. That is not a that is not an algebraic expression. This is not math. This is computer science. Computer science is math, yes, but they're different. In math, you use a single equal sign to say that the thing on the left-hand side is equal to the thing on the right-hand side. In computer science, we use that as an assignment operator. It means take the thing on the right-hand side and put it into the variable on the left-hand side. Right? Arguably, they misused and abused the equal sign. That was they made their mistake 40, 50 years ago, and we're still living with it today. Arguably, they should have used something else, and some languages do use something else. Some languages use colon equals for the assignment operator. Some languages use a pictorial of an arrow. Take the thing on the left-hand side and put it into the thing on the left-hand side. But most programming languages, unfortunately, use the single equal sign. Right? There's something else that we can use for testing whether or not two things are equal. But again, the assignment operator, and I'll write that down in the notes here below, the assignment operator means put the value on the right-hand side into the variable on the left-hand side. So consequently, the thing on the left-hand side, it cannot be it has to be a variable. It can't be anything else. The thing on the right-hand side, the left-hand side must always be a variable. The right-hand side can be a variable, a constant, or a literal, or an expression. Right? So what do I mean by that? Well, we can do various different things. I could say int x is equal to 10 plus 5. Right? Those are too literal. Here, I'll do it this way. Let's go ahead and declare x. I can set x to a literal value. It just means, i.e. a hard-coded constant value. I don't want to say constant because it doesn't mean constant, but x is equal to 10. There we go. The thing on the right-hand side is just a literal value. It's 1, 0. And that is base 10 because we are programming in human here, and humans count base 10. That's not 1, 0 in binary. You can set values using hexadecimal and other systems, but we're not going to do that. You can set x to be the value of another variable. So, for example, I could say int b is equal to 20. I can say x is equal to b. Right? Note, this only places the value at the time, value at the time of the assignment. It does not marry the two variables. Oh, I'm going to have to go to the next line. There we go. Meaning that all this is saying right here, x is equal to b, is it says take whatever value is stored in b at the time that this is executing and place and copy it over into this variable x over here. It doesn't mean that if I ever change the variable b again, that x is automatically changed. There's no connection there between x and b anymore. Right? X takes on the value of 20, and if I end up changing b later on, then x is not changed. B is equal to 42. X is not changed. It is still 20. Okay? Some questions here. The notes will be posted later after we're done. I'm not posting them right now, but they will be posted later tonight, along with the video, of course. All right? You can also do an expression, right? So I can say the right-hand side can be an expression, right? So for example, if I've got int a is equal to 10, b is equal to 1, and c is equal to, I don't know, something small, 4. I can say int r is equal to negative b plus square root. There's my square root value from the standard library. I'd have to bring in the standard library to the standard math library, excuse me, to actually use that value. Plus square root of b squared, b times b, minus 4ac, all over 2a. Right? Now I'm going to have to put parentheses everywhere. Why? Something that we'll talk about next week that you already know all about. PEMDAS. Right? Programming expressions follow PEMDAS. Right? Parentheses. Help me out. Anybody? Parentheses, something, multiplication, division, addition, and subtraction. What does the E stand for? Somebody go ahead and post that for me. Exponent. Okay, thank you. I don't know why that's necessary. Unfortunately, there's no good way to get an exponent in C. You'd have so note there is no native exponentiation in C. You have to use exp. That's a function. You can or actually no pow, sorry, for x to the y, for x to the y. Right? So if you want to compute x to the y, there is a pow function that stands for power. That is in the math library, and you can use that if you need to take 2 to the 58 or something. But of course, that's too big. That's not going to be representable by an integer. Right? Yeah, you can't use the carets. You can't, i.e., you cannot use the caret, or however you spell that, caret of x to the y. That does not work in C. Okay. All right. Take a few seconds here. That's where we'll end it. I don't see any outstanding questions on here. So I will wish you a good weekend. Well, I guess a good hack session tomorrow. Remember that is due on Monday. Your first reading is due on Friday. Again, if the bookstore cannot get it resolved by then we will make arrangements. But otherwise, your second reading is also due on Monday. So make sure that you're reading the Xi books. All right. Okay. Well, then, if there are no questions, no. So if you put x equals b after b is equal to 42, then yes, it would change it. Yep. You can also try it out. Write the program and print it out. Read ahead for how to use printf, which we'll cover on Tuesday. All right. Well, I won't see you until Monday, so do have a good weekend.